talk a bit about our progress in fully textured perovskite silicon tandem solar cells. And finally, I'll talk about how we try to upscale the deposition of perovskites in order to make real big modules in the near future, hopefully. Okay, so let's quickly recap what we know about reflection. So on the top right side, you can see the interface between air, refractive index of N1, typically around 1, and the perovskite, refractive index N2, typically around 2.5. And what happens is, under normal incidence, we have a certain amount of reflection. This is described by Fresnel law. And this doesn't just happen on the normal incidence, but also at different angles. And then the equations get a little bit more complicated. In the end, we always have Snellius and Fresnel law that dictate how the light propagates before and after the interfaces. Now, I was initially talking about flat interfaces. Life gets more complicated in real devices, and it also gets a little bit more helpful because we can use textured interfaces to reduce these reflection losses. So on the lower left side, you can see an AFM image of a zinc oxide layer that we grew here in Neuchâtel. And I just indicate roughly how the light could possibly, well, be deflected and then partially absorbed, for example, and how much light is then lost at each step. And after each iteration, you have even less and less reflection. And like this, after, let's say, 10 attempts, the light is not, or the majority of the light is not reflected anymore, but only about 2 or 3% are still reflected. So it's quite useful to bring textures into the system. This helps not just with reflection, but it helps with another aspect that appears in solar cells, and that is interference. So here's a EQE curve that I simulated with a transfer matrix tool from Ljubljana. So Marco is here, I think. In case you have questions, either you ask Marco Jost or Benjamin Lipovšek. They invented and used these tools quite a lot. And what you see is that there are these bumps and small shoulders. And these are a consequence of the fact that there's interference. So I want you to focus on the 700 nanometer illumination range. So the right, wait, just give me a sec. Didn't use the spotlight so far. So on this part here, and that corresponds to the orange line on the right side. And what you can nicely see here is that the light that initially goes into the solar cell entering from the left is reflected at the electrode, and thereby the incoming and reflected waves, they interfere, and this gives then rise to this bump here and the shoulder at 700. And this typically appears if you have layer thicknesses on the order of the wavelength of the light, which is exactly the case in perovskite solar cells. You can get rid of that by breaking this coherence, so by making the layer incoherent. That is very easily done in a simulation, but sometimes not so easily done in real life. All right, to do so, we used some old tricks that have been used quite heavily in microcrystalline silicon. Namely, we grew zinc oxide with a low pressure CVD process. And by tuning the parameters, that means the temperature and the gas fluxes of the precursors for zinc, that is diethyl zinc and oxygen. In this case, you can tune the morphology and dictate in which direction the zinc oxide then grows. And you can see here at the relatively low temperature of only 190 degrees and a relatively high rate, you get some surface roughness, RMS of around 8 nanometers, and the peak to valley, so the maximum difference between peak and valley is around 60 nanometers, so well below the perovskite layer thickness. You can drive that even further, and then you have a very high roughness. But so the perovskites that we process from solution are typically 450 nanometers, and then you may run into problems that you cannot fully conformally cover these. So what we sought and used was then something in between, in the middle that you can see here. And with these, we then constructed solar cells. So you can see here a cross-sectional electron microscope image of such a solar cell. The greatest part is the glass, then there's some zinc oxide. We interject a small layer of aluminum oxide. The reason being that the ITO that we grow on top seems not to be perfectly impermeable. So we saw some side reactions. Those people that have tried to work with zinc oxide and perovskites before, or are carefully follow the literature, know that zinc oxide tends to react with the perovskite in such a manner that you end up with just lead iodide or lead bromide. So it's very reactive. So we had to interject that. And on top of that, we then spin coat a perovskite layer. It's a triple cation, the one that is very heavily used and got famous by the initial paper by Michael Saliba. And yeah, you can nicely see how it covers these textures. We finished the device by thermally evaporating C60, depositing tin oxide from ALD, and finally the top electrode silver. The devices, in comparison to the planar ones that we did here, they had very similar, so these are the best in classes, had very similar open circuit voltages and fill factors. The main difference between the two, which is then also reflected in the efficiency and an efficiency gain of above 1%, is that the current is increasing. To assess whether the zinc oxide has any implications on the potential of these solar cells, so without the resistive losses, we did intensity-dependent VOC JSC measurements, and with these you can reconstruct a pseudo JV and assess what the maximum fill factor is that this optical stack could give you, or efficiency likewise. Okay, now we were talking about how to get more light out of with the system out of the illumination source, and a typical measurement that we do there is IPCE or EQE PV. And on the top right side, you can now see here the EQE PV of the samples with zinc oxide in blue, and the reference in gray. And this is then compared to a simulation that was likewise done in this optical simulation tool, CROM, that you can get in Ljubljana. What is quite striking is, so for one, the planar simulations and experimental results are extremely close together. The same holds true for the textured one, the nano-textured one, even though there's a small discrepancy. But what is quite interesting is that we get well above 95% in the important range, let's say. And overall, if you take the maximum current that you could get at this band gap, and you compare the current that we get from the integrated EQE, we are somewhere in the 94-95% range. That is on par with the best EQEs that are out there, which were produced with nanotextures, regular nanotextures in the group of Steve Albrecht and Christiane Becker by Philip Tockhorn. Not sure if he's listening, but yeah, check out that paper if you haven't. So that's the highest currents you will see out there. If we look into the EQEs a little bit closer, there are two regions. There's one that is shown here in red, where the zinc oxide samples actually outperform the planar quite significantly. And then there's another one where they are actually a little bit worse. That is due to the absorption of the zinc oxide primarily. So in the gray case, we don't have any zinc oxide. In the blue case, we do. And we first thought, okay, well, maybe we should get rid of that parasitic absorption by making a replication of the zinc oxide. But then a little bit of digging into literature let us think that maybe that's not a good idea after all, because this is the UV part of the solar spectrum. And people that closely follow literature may have come across this paper where it was shown that if you illuminate, in this case, methyl ammonium lead triiodide with green or blue light, you may get a degradation if you use UV light, whereas you get a PL enhancement due to, I don't know, ion rearrangement effect if you don't. So we thought, okay, maybe the zinc oxide can even act as a UV filter, and these results are not there yet. So we have the first couple of data points, but the idea is there. The UV soaking is underway, and I hope the next time we see each other, I can tell you whether this hypothesis worked out. Okay, so this is about zinc oxide. So the question next is how can we get even higher currents? Again, some optical simulations. In this case, I varied the roughness of the underlaying texture. So there's a little bit extra beneath the glass, so don't be fooled. I not purposefully, but I omitted that we have here some extra anti-reflection coating. Otherwise, you wouldn't be able to go so high in EQEs. What is important to take away here is that you need to overcome a certain thickness in order to really reach the maximum potential of the perovskite absorption. And this can cause problems. So I have here an example that is a couple of years old from our lab, where Florent tried to spin coat a perovskite on top of silicon. So these are then textures that are exactly in this range, so micrometers and above. And what you can see is that there are spots where the coverage is not very good. Recently, there have been a few demonstrations that you can do that. So the textures were a little bit shrunk in order to enable this. And then Yihu, I assume Yihu had the idea to spin coat multiple times to get a sufficient layer thickness to then fully cover the perovskite. The problem with that is a little bit that it's not ideal for the silicon. Yeah? So the reason why we need these big textures is that we want to reduce the reflection in the silicon also. And also, if we think in the long term, it's not exactly an industrial standard to make these tiny pyramids. So now we will shift onto tandem devices, tandems of perovskite and silicon. And I'll start again with a simulation. So you can see here the simulation of current matching conditions for perovskites with different band gaps and how thick you would have to make them in order to reach current matching. And what is maybe important to note here is, okay, at a given thickness of, let's say, a micron or so, you may run into collection issues because that's the typical diffusion length of lead halide, of carriers and lead halide perovskites. Nevertheless, I mean, many of you probably know that in this region, the recent world records were reported, so 1.67, 1.68 electron volts band gap, and the numbers are very close. And the reason being that I used pretty much exactly the assumptions that were fulfilled in these papers, namely a fill factor of around 80% and the open circuit voltage that is reduced by 240 millielectron volts due to non-ideal emission. Okay, so just as a comparison, our previous tandems had an absorption profile pretty much exactly following the one that I got from simulations. So that's a good sanity check, and tells us that the simulations and experiments are very close together. The way we make the perovskites onto these textures is we co-evaporate what we call a lead halide template. There we evaporate cesium bromide typically and lead iodide. And then we spin coat an organohalide solution made out of methylammonium iodide, formamidinium iodide, or formamidinium bromide, and a few more. And then we anneal, typically outside of the glove box, so under humid conditions. And like this, you can see here on the right side, we start from the template, and it swells up because of the extra organohalide, and we can do this in planar configuration, but also in tandems, and conformally grow perovskites on the tandems. The problem with that is that, or one of the problems that we witnessed was that when we stick to a small thickness of only around 350 nanometers, we get a rather good performance, high fill factors, very good open circuit voltages. However, if we try to go for textures and make the perovskite thicker, all of a sudden we really lose in fill factor. And we tried to look into the origin of that. And upon looking at cross-sectional electron microscopy images, we saw that there are these domain boundaries. Yeah? So many people would call those grains. I'd rather stick with domains. You can see these domain boundaries. And I mean, in the end, charge transport must occur, well, not exactly vertically, but at least the tendency should be vertical. Yeah, so how exactly we don't know, but either it's perpendicular to the substrate or a little bit bent, most likely. And then you have to go across several of these boundaries. And this may impact the collection efficiency. One of the first tests we did was to vary the annealing temperature in this second step, so after organohalide deposition. And what we saw was that, okay, if we go higher in temperature, we can increase the domain size quite drastically. However, there was a problem, namely that increasing the annealing temperature also had the side effect that we removed part of the organohalide again. And this you can see here. We have an X-ray diffractogram of the prototypical perovskite, so around 14 2 theta, and of PVA2 around 12.5 2 theta. And what you can see is that we have a slight increase in crystallinity in the perovskite, but a drastic increase in PVA2. And that will impact the charge transport likewise, because PVA2 is a wide bandgap material. And it also negatively impacts the stability of the perovskite, as has been nicely shown by Van Fu in collaboration with Empire, I think, well, 2 years ago already. So the question is, can we find a workaround? And we did. So postdoc in our group has come up with an additive. I am not entitled to tell you which one it is. You'll have to read up on that in a couple of weeks, hopefully. It's a tiny additive in the second step, and it does the following. It helps us with a passivation. So we see that the temperature helps, but then even above that, adding this additive increases the photoluminescence efficiency and thereby the potential open circuit voltage of the whole system. And even more importantly, it enables us to reach these high temperatures or use these high temperatures for annealing without a drastic increase in the PVI2 concentration in the perovskite. So we are able to anneal hotter without producing as much PVI2, and our initial hypothesis is that we somehow seal the surface against this evaporation losses of the organohalide ions. To make this a little bit clearer or more quantitative, you can see here the relative peak times area, a comparison between the PBI2 and the lead iodide for the different temperatures. And clearly with surface passivation, we are more resilient to high temperature annealing. Okay, in the end, we want to make good solar cells. So what came out with the solar cells? What we saw is, indeed, these higher temperatures with the additive enabled us to anneal at high temperatures and not lose fill factor, but quite the contrary, improve the fill factor. We had a tiny bit of a loss in the open circuit voltage, around 30 millivolts, but this did not translate into the voltage at the maximum power point, which is the same thing as the fill factor in the end. Yeah. So overall, an efficiency improvement. And you can take a look at that and try to explain the mechanism of that. And we did so. In dark blue, again, just a JV curve. Then as before, the sun's VOC, so VOC JSC as a function of intensity, reconstruction of the JV curve to quantify the losses due to transport. And then finally, now a technique that Martin and I developed while still in Potsdam, or not developed, but used in perovskite. We measured the quasi-Fermi level splitting of the perovskite layer without C60, so removing one of the charge transport layers, and thereby got the quasi-Fermi level splitting, and did that as a function of light intensity, and thereby you can again quantify the potential of this semiconductor. And what you can learn from that is basically that, okay, we have removed quite a bit the resistive losses by this high temperature annealing, but we didn't remove the interfacial recombination losses. So interfacial recombination is still the problem. So we could, in principle, go a little bit higher in fill factor, but well, this loss here also translates to a loss in transport and extractability of these charges, so recombination loss around the maximum power point, which we haven't solved yet. I think for tandem applications, if you're not able to remove C60, there will be, apart from the cost issue, we'll never reach the full potential of the perovskites. But this we'll have to solve at another day. All right, so taking another look at the morphology. I've shown you before that the higher temperature annealing gives rise to a better morphology in terms of the domain size. And this also translates into less domain boundaries across the layer thickness. Okay, finally, let's take a look at the tandem performance. So when we actually use these in tandems, so as said, we get an improvement in fill factor. The VOC stays basically the same. And what is noticeable is that we got quite highly efficient tandems. So we get a very high current, impressively high. I think this should be on par with the highest reported ones, if not exceeding them, and a stable 28% maximum power point efficiency with EQEs that look like the red and blue one here on the lower left side. And I mean, I think this is as good as it gets. Yeah? So this looks like a simulation, but it's an actual measurement. Okay, so now the question is, what can we do? So the devices that I've shown you and the ones from HZB, so this is a tandem on tour that now has gotten famous, at least for the people that do tandems, by Köhnen. It's typically around 1 square centimeter. Ours look more like this, so they are 1.5 centimeters square. But in the end, we want to have something like this. And the question is, how can we get there? And let me quickly show you an approach that we take. So there are different approaches. Overall, many people now think of high vacuum thermal evaporation, co-evaporation, either as a co-evaporation or sequential. The advantage would be obviously that there's high uniformity and purity. And in theory, so if we would ask people that make OLEDs, they would say, yeah, it's very controllable. But the problem is the organohalides. Yeah? So they don't evaporate in a normal fashion. It's not a ballistic process. They dissociate and then reassociate, increasing the pressure and making it very difficult to nicely deposit them. And that then also entails that there is probably a relatively irregular growth. And this makes the rate monitoring extremely difficult. So it's rather difficult to master. Some groups have managed. There are fully evaporated perovskites of different kinds, but it seems like a rather complicated process. And so we try to avoid that. And so the idea for us is we want to use vapor transport, where we first evaporate the lead template as shown before, and then we transform that into a full perovskite by just transporting the organohalides afterwards. And the idea is to have a better control of each step. Yeah, so we will use a concept that is very similar to a tube furnace. The problem with tube furnaces are, of course, that there's a rather big, at least concentration gradient. You can see here one of the first papers, I think it's from 2015, where they used vapor transport. And you have different situations, even across only a few centimeters. So you can run from a system where you have an undersaturation in the back, so position A, to a heavily oversaturated within less than 10 centimeters. And if you want to make a sample that is bigger than 10 centimeters, you will most likely have a concentration gradient across that, which is of course not something that we want. So our idea is, as said, we will first evaporate this lead template, and then so far we always spin coated the organohalide solution, but because this is not scalable, we came up with a new solution. We call it a Björnet, in reminiscence of the postdoc who initially built that. And it's a showerhead configuration where we have a thermal evaporator with nitrogen flux. We heat the organohalides and then transport them through a tubing system and dispense them onto either many different samples or big samples in a vacuum chamber that is heated or cooled. Okay, let me quickly show you how that system looks. So we have an evaporator. So here we have the organohalide salt that is evaporated with the carrier gas running in, grabbing up the organohalide vapor, and then dragging it into the deposition chamber, where here on the top, you can't see it just now, is a shower head, and here we have the sample stage. The nice thing about that is that we can nicely separate the sublimation and the deposition of the organohalides. So we don't worry so much about the inconsistent pressure close to the evaporator. We have a relatively big shower head system, so we can go into industrially relevant sizes of M6 wafers or 6-inch wafers. And we have quite a lot of control. So we can control the pressure, the flow rates, the temperatures of the different parts. So the tubing, the heater, the walls of the chamber, and even where the sample sits, and quite a few more. Yeah, so to explain these, great. We have a lot of parameters to play with, and I want to show you an example. If it moves, yes, I want to show you an example that was used to demonstrate the feasibility of this approach. So we started out with a very simple one. This was a paper that was written when I just arrived. And what you can see here is if you preheat the sample on the heating stage, you can control the amount of perovskite that is forming. So if you have a too low temperature, there will be parasitic condensation before the methylammonium iodide ever reaches the sample. If you then increase, you slowly see that the perovskite forms, and at a preheating temperature of the gas of around 150, you can see that perovskite forms until the iodide is gone, and this is then also visible. Yeah, so we form a perovskite, nice black film, whereas the other ones stayed rather yellow. So the template is PBI2 dominated, so that stays yellow. Similarly, you can tune the transport temperature, and a similar thing occurs. Yeah, so we remove the possibility of the methylammonium iodide to parasitically condensate and transport that then onto the samples, and finally we manage to get a perovskite if the piping temperature is high enough. I won't bother you again. The same story. So you can of course also change substrate temperature and hence modulate the rates of condensation and interdiffusion and again evaporation. And upon tuning this properly, you can get a nice perovskite film that then gives you a device, yeah, with mediocre performance, but it works. So this was a big step forward, that we got a device that works. And what is the most important thing, and also the goal of this project, is that we can really nicely cover M6 wafers. Yes, on the lower right side, you can see a size. This is an area of around 250 centimeters square. So if you manage to conformally grow on these length scales, then you're good to go for industry. Now, methylammonium is maybe not the best candidate in terms of stability. So we wanted to expand that to form a medinium iodide. It's very widely used. It seems to be thermally more stable, but with all the parameters that you saw before, so all the temperatures, fluxes, everything that we tried, we couldn't get this to work. It stayed yellow, whatever the conditions. So we set out to understand this problem. And to do so, we looked at whatever condenses on the perovskite. It was redissolved in deuterated DMSO and measured with NMR. And with NMR, you can take a look at which kind of molecules end up being deposited on the surface. And what we found is, okay, there's formamidinium iodide and ammonium iodide in a quite drastic ratio of 1 to 230. So there's way more ammonium iodide than formamidinium iodide. And this is not exactly new. There have been a few reports again, a couple of years old, that looked at what happens to formamidinium iodide if you anneal it or if you heat it under mild vacuum. And what people saw is, yeah, indeed, almost immediately, even at low temperatures, you see ammonium or ammonia forming. You see thiophene forming, and a more complex molecule, which is called zimtriazine, and only a tiny amount of formamidinium. So a prototypical decomposition route would be something like this. So we have a formamidine that then builds this cyclic molecule and releases ammonia on the way. And this ammonia then can react under a proton reaction with hydroiodic acid and form this NH4 iodine that we just saw. So the question is, can we also invert this chemical reaction? Yeah? So for chemists, this is maybe something old, but to me it was quite interesting to see this happening. So the question is, can we change the chemical equilibrium? Yeah? So can we invert the reaction? And the answer is yes. So we used an ammonium-rich gas instead of nitrogen. Ammonia instead of nitrogen, we used ammonia as a carrier gas, and all of a sudden we could tune that ratio between formamidinium iodide and ammonium iodide being deposited and improve that by more than an order of magnitude. And that means that in contrast to the layers that we saw before, so here we had an exposure to supposedly formamidinium iodide vapor over the course of 8 hours, and we could not really see a reduction in PBI2, maybe a little bit, and a tiny bit of perovskite, which is also the reason why it turns slightly darker after 8 hours, but that's not a time scale on which you can work. In contrast to that, when using ammonium as a carrier gas, we could at least reduce that time by a twofold, and probably even faster upon tuning. So that already brings me to my conclusion. Not sure how I'm doing on time. Oh, it's still okay. So in the first part, I've shown you this low pressure CVD deposited zinc oxide, which allows us to make 20% efficient devices with a very nice spectral profile, reaching 94–95% of the maximum current. By using a passivation strategy, we were able to get pretty efficient, close to world record efficient tandem devices with very high current density, combining the two subcells. And in the last step, shown you CVD, not CDV, pardon, a PVD-CVD system that we use in order to scale up the processes that we initially developed. And we managed to get large sizes and, well, let's call them mediocre proof of concept efficiencies with methylammonium lead iodide. And in the very last bit, I've shown you that formamidinium iodide, although it's probably a more stable organohalide per se, under the conditions where we use to deposit it, it decomposes in a big zoo of chemicals. And by changing the amount of chemicals in the system, you can in fact still get a formamidinium lead iodide perovskite, but this is still ongoing work. With that, I want to thank all my co-workers here in Neuchâtel and the funding bodies, in particular Peter and Xinyu. They are mostly responsible for the tandem data that I've shown, and Florent and Quentin Guisnet, they are responsible for the Bjornet for the CVD system that I've shown you in the last part, and of course Quentin Jean-Gros and Christophe Palif, and all the other people here in the PVLAB in Neuchâtel. And thank you for listening, and I'm happy to take your questions.